All right, this is ICP Unit 3, video number 3. So where we left off, we were just talking about how an atom can be compared to a ladder. So here we've got a ladder, and these are the rungs of the ladders, or the steps. So I'm going to use this to help explain the atom. An atom remains in its lowest energy level, known as its ground state, until it absorbs energy. Now, if you think about a ladder, most people don't like to climb up ladders because either we are afraid of heights, or we're afraid of falling, or we are afraid of hitting the ground. There's a lot less energy if you are on the ground than if you are on the top rung of a ladder. So an atom, when it is in its lowest energy level, it is in the ground state. Just like with a ladder, the lowest energy is the ground. When an electron absorbs energy, it jumps to a higher energy level. So this one was in the ground state. It is going to absorb energy, and maybe it will end up here on the second rung. The thing about higher energy levels, just like with ladders, higher levels are less stable. If you climb a ladder that is not the strongest ladder, the higher you go, the more you will feel it wobble. So the electrons do not want to stay at this higher energy level. They want to return to the lower level, which would be the ground state. And so the electrons will fall back. So here the electron is falling. And as it falls, light is emitted. This is how the electron loses some of the energy required for it to come back down. So it's falling, and here it is letting off some light. So this is maybe what light would look like coming off of it. The specific wavelength of light corresponds to how far the electron fell from the higher energy to the lower energy. So this one in my picture fell 2 rungs, and it let off some yellow light. Let's say that it only dropped 1 rung. Maybe it let off something lower energy like orange. Or let's say an electron fell from the top rung to here. That is a long way to fall. That's a lot of energy. And let's use purple. Purple light has a lot of energy. So Bohr's model explains some things, but it's not perfect. So it works. It works for hydrogen atoms anyway, but it doesn't explain any of the other elements. Now, at the time, there were fewer elements than we have now, but we knew about a lot of the lighter elements: hydrogen, helium, lithium, beryllium, and so on. At least the first 18 were already known about, so the fact that it only works for the smallest atom, hydrogen, kind of a shortcoming for this model. But at least it works in one scenario. Bohr also couldn't account for the differences in the chemical behavior between the elements. Why does one act differently than another? Another thing about Bohr's atom is that it had circular orbits. If you think back to the previous unit, so let's say here's the nucleus with its protons and neutrons. Here's an orbit, here's an orbit, here's an orbit, and the electrons are going around these circular orbits. And this is a model that works, but it's not really the most accurate either. In reality, the orbits are very complex shapes, definitely not circles, and they move in 3 dimensions. We use the Bohr model from time to time because it's easy to draw. A few circles, a few dots, you've got your Bohr model, and for the person who comes along after you, this is a fairly easy thing to read. Remember, the whole purpose of a model is to help us understand a more complex idea. So while, yes, the atom is more complex than this one helps us understand what's going on pretty well. So it still works in that situation. So we compared energy levels to the rungs of a ladder. The electrons have to stay within an energy level. An electron cannot exist between energy states, just like you can't stand in the space between ladder rungs. So I'll draw another ladder. Here it is. If you are going to climb a ladder, your feet could go something like this. So here you are on the ground, and you put a foot here, put a foot here, you put a foot here, you put a foot here. They are standing on the rungs. Here's what's not going to happen though. So here's your feet on the ground. So I step on the first one, sure. And then I put a foot here, and a foot here, and a foot here, and a foot here. It's not something that works. If I'm going to climb a ladder, I put my feet on the rungs. I can't be climbing the space in between. So when electrons have enough energy, they can go to the next energy level. So let's say we're going to bring up this foot right here. If you don't bring it up high enough, meaning not enough energy, and it's here, it's going to end up landing on this rung. And you're going to be a little bit startled. Only when it has enough energy, so we're bringing it all the way up here, now it has enough energy to get to this rung, and it can stay there. When you bring up your next foot, if you try to put it here, again, you're going to fall down to here. It's only going to stay on a ladder rung when it has enough energy to get to the next one. Same with electrons. If we're looking at this Bohr model of the atom, so here it is really simple. We've got a couple of electrons here. We cannot have an electron here. It needs to pick an orbit. It needs to either be here or it needs to be here. It can't just sit in the middle. Chances are if we had one here that was in the middle, it's going to fall back down to here because it didn't quite have enough energy to go up the ladder. Electrons will remain in the lowest possible energy level until they are excited, until something makes them climb the ladder. Excited electrons emit light as they return to a lower energy level. Next idea is an orbital. Notice the difference between this is an orbital, and what you see here at the top where it says Bohr's model had circular orbits. An orbit is a circle, an orbital is not really a circle. It's just an area where an electron is likely to be found. It doesn't mean it's there. It's just this is where it's most likely going to be. if you came into school and you wanted to find me, I spend 90% of my time in my classroom. So if you want to find me, that's the best place to look. Look in my classroom. But the other 10% of the time, you might look across the hall, you might look around the corner. But 90% of the time, most of the time, you're going to find me where I'm supposed to be, where I'm likely to be found. An electron is going to spend 90% of its time in this orbital area. When we're talking about orbitals, there are a bunch of different orbitals. Any individual orbital can contain a maximum of 2 electrons. An orbital could have 0 electrons, it could have 1 electron, or it could have 2 electrons. In the current model of the atom, each energy level is divided into sublevels. An energy level is composed of somewhere between 1 and 7 orbitals. And remember, each orbital can contain up to 2 electrons. So I'll give you a quick sketch here. Let's look at an atom that has, we'll use neon. So we'll say let's do the Bohr model. So here's neon. And according to the Bohr model, and I'm going to tell you that we have 11 electrons, just to make this easier. So here's that's 10 electrons. Okay, let's try this again. So here's 2, 4, 5, 6, 7, 8. This is how you might represent neon with 10 electrons in the Bohr model of the atom. And let's label it the Bohr model. There we go. This is nice. It's easy to read. It's easy to draw. If you came behind me and looked at this, you could say, yeah, it's neon and it's got 10 electrons, and simple enough. The current model of the atom is not really as simple, so we don't spend a whole lot of time trying to figure it out in this class. So let's say that here's the nucleus, there's my neon, and it still has 10 electrons, but it's got energy levels and sublevels. So in the first energy level, I have this, let's see, what color should I use? Let's use orange. So I've got this place where I can have 2 electrons. So here's kind of this sphere, this ball-shaped area where I could find 2 electrons. And then I have an area where I might find 2 more electrons. And so this is another big circle, this big ball area. And so far, these two are matching up okay, I would say. Because you've got this inner circle with 2, you've got this outer circle, which only has 2. But then it gets kind of weird. So then you get this, the next 2 electrons are going back and forth in this sort of a pattern, like a figure 8. And then the next 2 are going this way in a figure 8 sort of thing. And if you're using a pencil, you might not want to draw this. It's just going to make a mess on your paper. And then one more, so let's make it red. And then one more, so maybe something like this. And it's really messy in how you draw it. So if anything, the current model of the atom shows you that it's probably more complicated than the Bohr model, and it's also not really nice to draw on paper.